I'm looking at our grades on our assignment.
Probably sometime this week.
Yeah, I hadn't checked yet. So
yeah, no, it's not. They are not ready yet. I'm inclined to say more towards the end of the week because we had a kind of busy week. I have a kind of busy week. Can you hear me? Can you hear me? Hello. Testing, testing. Motion, baby. Testing, testing, testing. Can you hear me? Yeah, the Camtasia again. You need to be careful when you pop up. It again started with not the full screen and the mic.
I would have needed, yeah.
Oh yeah. Yes. Honest.
Seems
Yes, errors.
that's errors.
Is he using the include ones or not?
Oh, and then he has to.
Oh yeah, or define the preprocessor bar. Either of those will.
Actual. Oh, no. Has to. Good when you don't.
Okay, before starting, any questions from last class or previous classes or the assignments, something? Oh, it's good. Okay, just a reminder, next week on Wednesday, we will have the intro to Signit. So for those of you who are not familiar with the systems, I suggest you to take a look at it. It's 1 hour, but not to take a look, but to come to the intro is on Signit office. And especially because in a couple of weeks, we are going to start using Signit to develop parallel programming strategies, right? So it will be a nice idea to have an idea of how it works and how to compile on Signit and how to run things on Signit, okay? And immediately after, there is free pizza as a lunch. And
if you sign up,
yeah, no, you are not allowed to eat. And we will have a tech talk on visualization, probably. So, very likely. So for today, we're going to discuss data structures, okay? And the plan is to review a bit the basic types. Rancis mentioned them in the first or second lecture. Then we're going to see some structures per se, some more dynamic and complex structures like lists, stacks, queues, trees, and maps or tables, hash tables, essentially. At the end, I hope that you get the idea that when you develop a code and when you're trying to find a solution for a problem, one of the most important things to think about at the very beginning is the abstraction process of understanding what the problem is and how to solve it, but also define the data structures, define the type of variables, the type of data, how to store your data, how to deal with your data in order to solve the problem, because that will help you to solve the problem more efficiently, more robustly, and in a better way. And we have a slide at the end trying to emphasize that. Okay? So let's quickly review the very basic types of variables, if you want, that we have in C++. So we have primitive types like booleans, logic variables. We have numeric types like integers, short, long, very long ones. We have floating points, again, different precisions, float, double, long double. Complex is you use the standard libraries. We have characters or a string of characters. And finally, we have some what are called composite types or abstract data structures types. Examples of those are that we have seen are actually arrays or pointers. We're going to take a quick look or a deeper look today at them. And then we have other structures or other constructors like classes, more kind of object-oriented structures. A structure itself that will allow us to combine different types. So far, each of those, even when you have an array, is of a unique type. It's only one type of object, right? One type of variable. By using the structures, we will be able to combine an integer with strings, and so on. Enumerate types and units. Okay. So let's review a bit the idea of pointers. We mentioned this in the first or second lecture. Let's say that we have an array of 3 elements, 0, 1, 2, and then I'm creating a pointer. And the way to think, or one way to think about pointers is just an address in memory, a physical address of the memory. So the array has the elements 0, 1, 2, and then I can think of, okay, accessing the first element by defining the pointer and assigning it to the array. I can think of accessing the first element by just looking at star PTR, which is the pointer. I can do actually arithmetic with the pointer and say, okay, because I know that the pointer is of a type array and is an array of integers, then by doing plus plus, PTR plus plus, I will be accessing the next element, and so on. Okay? So the point is that by doing that, we have direct access to the information that is stored in that structure in the array. Okay, so it's a different way to access. We have been accessing the array by just identifying the index of the array. But if you define the array through a pointer, you can actually access the content of the memory through the pointer. Okay. Structures will allow to combine different types, as I mentioned. Like the way to define is, okay, you use the keyword struct, then you define the name that you want to give, like a nav variable. You open braces, and you put all the types of variables that you want up there. For instance, there I having an integer, weight, and a double price. Okay, and the structure is called product, right? Then I can start to define variables associated with that structure. So it's like I'm defining a new type of variable, and this type of variable is a combination of different types. Then I have a product apple, I have a product banana, and melon. Okay. I can do the same definition by just saying the structure, and then immediately after the definition, mentioning the variables I want to assign to each of them. Okay? And then you will say, okay, how I access the property. So now I have this new type of variable that combines 2 of them. The way to access this is, okay, you have the variable now, take apple, for instance, and then dot, and then the property, weight or price. Okay, is that clear? So the structure basically will allow us to combine different kind of variables, and then within each of them, we can access the property by just doing dot and the name of the variable that we define. This is a very short review or mention, if you want, of classes and objects, and will be more on next class, I think. But basically, the idea that I want you to keep in mind, we are going to use some of these functionalities today, but the idea that I want to keep in mind is, okay, I can define an object and defining the class stone weight there, and then there are different things you can do with the object. And one of the most interesting things that you can do is that you can define methods associated with the object. Okay, some of those methods are private, so it can be accessed only by the object itself, and some of those methods are public, and it can be accessed through the code all around. Okay. So in this case, the private part has the structure of the object, has the properties of the object. It has an integer that represents the weight of the stone, and then it has another integer, another variable, a float, that represents the fractional weight of the object. Okay, so it's the integer part plus the fractional. And then I have other methods associated that I can define for the object that can be accessed from outside of the object, like set the values of the properties of the object or show the properties of the object. Okay, and how I access it? Well, because I define the class stone weight, I can define a variable associated with that class, my weight, and then I can use the method set stone weight to define the values, and then I can just show the values. Okay. So what I want you to remember for today is, okay, I can define an object, I can define the properties in a similar manner as I define the structures, and in addition to that, I can define functions that will apply to the object. If those functions are accessible through the code or outside of the object, it depends if you define in the private or public part of the object. Okay, any questions? So let's look at an example. I have an example here of an array of structures. So we saw the array on the one side. We just saw the structure that will allow us to combine different types of variables. But let's see an example that combines both things together. So I'm defining here the structures movies underscore t. Basically, I have a string that is the title of the movie, and then I have the year in which the movie was produced. And immediately after, I'm defining the variable films. Okay? And I'm defining 3 elements there. So it's an array of structures. Okay? So now, instead of being an array of integers or an array of floats, it's an array of the structures that I'm defining. So each element of the array will have the properties defined in the structures movies underscore t. Then I had the prototype of a function, print movie, which I'm showing here. Okay, and print movie has the argument, so it doesn't return anything. It's a void function, but it receives one object of type movie style. Okay, so it's one of the structures. It has the type of the structure I just defined. And what it does is just print in the screen the title of the movie and in which year it was produced. Okay. And then the main code is just a definition of a variable that I'm using to read data for the title and another for the year. And then what the code does, it reads 3 movies. It does to enter the title. This function gets the information from the screen and fills in the title variable of the structure. It gets the year and it fills that in the year of the structure. Okay, and at the end it says you have entered a certain number of movies, and it prints the movies by using the print movie function. Okay, so when I run this, I compile and I run. I enter 3 movies: Blade Runner on 1982, The Matrix in 1999, and Taxi Driver in 1976. And the output of the code is, okay, you have entered these movies, and it says just the name of the movies and the years. Okay. So the example is basically construct a new structure where you have the title as a string, the year as an integer, and then you create an array of each type, of that type, each of them. Yep. That's right. Okay. Yeah, so you can think of it like this. So before we saw we have an array of integers, 0, 1, 2, right? Now, instead of having that, you have a tiny new record or a tiny new structure, which is the title, and then the year. And the same thing repeats in each of these slots. Okay, so this is the new type, if you want, that I created that is called movies move type. Okay. Yep. You mean this one? Let me see. Well, you could define it here, right? But you need n to vary somehow. Memory-wise, it may be, if the code ends here, it won't hurt too much. If the code goes longer, probably it's a better idea. If you are not using n anywhere else, just define it here, and it will die when the fork ends. And the same here, right? You have another fork. It probably was lazy, and I just put it there. But yeah, probably it's a better idea to keep them localized to the braces of the full state. Yep. Okay. Any other questions? No? Let's see another example. So we saw the arrays of the structures. Let's see now pointer to structures. Basically, the same structure I used before, the movies type structure. And now instead of defining an array, what I'm going to do is, okay, I'm going to use the movies type, define a movie. Okay, so now I have a variable of the structure, it's called a movie. And then I'm going to define a pointer pointing to that structure of the type that structure called pmovie. And what I'm going to do is I'm going to assign this pointer to the address of the variable amovie. Okay, so if you want to see, this is something I mentioned, I think, on the first lecture where we mentioned pointers. One very nice thing to think about pointers is to draw like arrows and the memory. So what I'm doing here is I'm defining a variable called amovie. Okay, so this variable, I'm assigning a pointer which I call pmovie. Okay, and the pointer itself is the star, which is actually pointing to the address, to the physical address of this variable. Okay, the content can be accessed by the ampersand, the variable, like in this case, amovie. So I'm basically saying, okay, the pointer will point towards the content of the variable. Okay, same thing as before. I'm going to request to enter the title of the movie. I'm going to get the line and then fill whatever it was entered in the title variable of the structure. Okay, remember this thing is a structure. Yep.
Asterisk is the actual thing arrow pointing at it.
Yes.
Then pmovie itself also is
Yes.
stored.
That's correct. So pmovie itself is the pointer. The star of pmovie is the actual arrow pointing toward the direction. The ampersand of that is the actual content of that direction. Okay, that's a way to think. So I'm entering the title. I'm filling the information of the title in the variable of the structure. And look how I'm accessing it now. I'm doing pmovie arrow title. So that's the way to say this is the field, if you want, within the structure that define pointed by the pmovie point. Right? I'm entering the year again. And now this is a way to transform whatever I input there into integer. And I'm filling that into the pmovie year. Okay? And at the end, I just printed that in the screen. Okay? So that's the output out there. The movie, the year, and again, the output from outputting that. Okay. One thing I want to emphasize is a bit of annotation, but it's very important because it depends or will affect how you write the code. So I mentioned I will access the field of the record or the structure title by doing pmovie, which is the pointer, arrow title, which is in some way the same as doing star pmovie.title. This notation we saw before. So this is the record or the structure, and this is the field of the structure, right? So basically what I'm saying is doing this arrow thing is the same thing as doing the parentheses and the star. And I will show you why it's important to emphasize the parentheses there, because this is different from doing a star pmovie title, which the compiler is going to understand star parentheses pmovie title. Okay, so in the first case is the pointer pointing towards the structure, and then the field in the structure. In the second case, the compiler is going to understand the pointer of the whole thing, thinking like the field inside the structure can be a pointer, which it can also be a possibility. It's not like crazy. We are going to see all the possible variations that we can create with this definition. Okay, but be aware of that, and be aware that using parentheses and using the arrows can be very, very useful for specifying what part of the structure you want to access. Yeah. So basically, you can say, let me go back. So this is the same. pmovie is a pointer, okay, and I can say pmovie arrow title, and basically what I'm doing is in the pointer. Now I have two fields here, title and year, okay, and when I do pmovie arrow, basically what I'm saying is from the pointer, give me the field title or year, okay? Or I can come back to the previous notation where I have the structure and say dots and the feature of the dot. So I could say, okay, because I want what is inside here, give me the start of P movie, and then dot, and it can be title or year. Okay, and that will give me access to any of the properties of the structure. Okay, but if I do this without using the parentheses, if I just do star P movie dot title or dot year, the compiler is going to understand this as having a parenthesis, the whole thing, and thinking that this is a pointer, which it can also be. This could be a pointer pointing to somewhere else. We're going to see that. So it's not crazy to think that I can have this kind of thing. So if you want to do that, you need to be explicit about using the parentheses to indicate that the first part is just a pointer, and within the pointer is pointing to a structure, to a variable of a complex type, and within that type there are different. Yeah, exactly. So the structure itself can have pointers. Is that clear? It can be a bit confusing at the beginning, but it's just the important thing is be aware of what is the structure, what is the underlying structure of the thing that you want to deal with, and then figure out if you need pointers or you need throw the pointer to access the fields of the structure. Okay? Questions? Okay. So let's see. Let's recap a bit. So we saw structures. Structures allow us to combine different types, different basic types defined in C, integers, double, strings, even arrays, and so on. We just saw examples of a pointer pointing toward a structure, and the structure again can be a combination of different elemental types. Okay. Now I just mentioned this. Imagine that we can have a structure that also includes a pointer. Okay, that is possible. So again, structures, pointer to structures, and structures with pointers. You can imagine how this continues. Because I have already a pointer that can point toward a structure, I can have a pointer that points toward a structure with a pointer. All right? So I have pointer to a structure, that's the example that we just saw before. And now within the structure, it can be also include a pointer. All right? This is going to get even better and better. What do you think is the next step? It's all there. It's like Legos. Now I can have concatenated these things, right? I can put one of these folks pointing to another structure with a pointer and so on. Okay? So basically what I have there is a pointer pointing to one structure, which has another pointer, and so on and so on. This structure, this type of structure, is called list. And if you want to think in the most simple expression, it can be seen as an array, but an array with a dynamical size, where I can remove and add elements at my wish. And this is also very powerful because you are not limited anymore to have a constant or a fixed amount or size in the array. Right? You can make it grow or shrink or clean or delete or add elements in the array or in the list. Okay, clear? We are going to see examples of how to implement that. So this kind of structures, in particular this one I just mentioned, usually are called linear data structures. They fall under the name of list or linked list because there's links connecting each of the elements in the list. And one of the simplest cases may look like this. So this is a structure, again, I'm calling node, it may be suggested. One of the elements in the node is the value, is an integer, val, and then the other element, and here is where it comes, the linking part, is a structure, which is of type node itself, which is a pointer. Okay? So basically, this kind of structures are recursive structures. So they point towards types of themselves. Okay? It's not pointing toward the same variable itself, but it's pointing toward a type of it that is of the same type of itself. Okay, so that's the node. So basically, this is the element. So if you want to think, is a value and a pointer towards something that is of the same type of the thing I am, the node. Okay, and then I define the object basically node. That's a similar way to define it with the value or the pointer toward the class node. Okay, so two different ways of defining as a structure or as an object. Questions? Clear? So this is allowed to do in C++. Okay, so let's see some particular cases of this. Again, this has a lot of applications, and you won't believe how fast you can make things run by just changing the traditional or fixed structures into this kind of dynamical structure. Of course, there is a price to pay, right? The price to pay is that you need to deal with the implementation and handle these elements. They don't handle so easily as fixed arrays. Yep.
So how does this start?
We're not going to see that yet, but I promise I will show you something at the end. Okay? It will for sure allow you to have dynamical things and increase. I will tell you more about that. Yep. Well, you are basically defining the pattern one way, but you are not saying how many elements. That's the part that we need to take care of, defining how many elements we want to add to the list. Okay, that's something that we are going to see as well. Okay, so basically you are just defining the model, and from there on you have that structure available to create further and further elements. Okay? So one implementation, one example of list is what is called a stack. And basically you can think as a stack of books that you put in your desk. Okay, comes one book, you put it, you read Physics 101, put it there, Chemistry 101 on top of that, and so on and so on. The reason why these objects or this implementation is useful is because then if you want to recover things, you basically are going to remove the last thing that you put there. And that kind of implementation is called LIFO, is last input, first out. So the last thing that you put in the stack is the first thing that you need to remove to access more things from there. Okay? So the last thing that you put on top of that structure will be the first thing that you take out. Okay? Usually there is a convention or a notation or I don't know, however you want to call it. But when you put something in the stack, it's called push. And when you remove something from the stack, you call pop. And the last part of the stack is called the top of the stack. Okay? So some convention, basically. I'm mentioning this because we are going to implement those functions, right? That's what we are going to do. The other thing is queues. Again, if you think about queues, again, it's one of these linear structures that they can grow dynamically, right? We don't need, you go to, I don't know, any place where there is a queue and you enter the queue from the back, and the first person to go out is the person that was in the front, right? So the queues is, again, it's a linear structure, but they work in a different manner as the stacks work. And the way to think about them is called FIFO, which is first input, first out. So the first person who arrives to the queue supposedly will be the first person to leave the queue. Okay. Again, the implementation, the structure itself is the same. It's the same structure, but the way to access, to push, pop, will be different according to what implementation I want to deal with. Okay. And then there are different combinations of those. There are things more complicated. There are things like double linked lists. Basically, this is kind of a list, but then I have pointers to the previous and to the next element. So it's double linked. I can access from the back or from the top, right? The advantage of this is these are a bit more tricky or complicated to implement, but I can go from the back to the top and from the top to the back without any problem. Okay. Then I can have circular lists where the last node points towards the first. And again, it's the same idea. I can very easily circulate that, or I can have both ended queues.
So how does that interact?
Well, in that case, you need always to have like idea of which is the first point where you enter the queue or the list, and then you can either circulate it. The idea is that basically when it's just for avoiding hitting the last element. Okay, when you hit the last element, you come back to the first. So it's not that will allow you to cover or to go through the list in both directions, but basically will allow you to come back to the first when you hit the last one. Some of them are maybe more useful for some cases or others. Okay. Any other questions? No? So let's see some examples of implementations. And I will show you the first example just for simplicity. I'm going to cheat, and I'm going to use arrays instead of these dynamical structures. Okay, but the idea is the same. It will give us some. It will be easy to show. Okay. So again, I'm going to define an object here, a class. It's called a stack. So remember, the stack is the last thing that I put is the first thing to leave the structure. Okay. And my class will have, basically my structure will have two elements. The array that contains all the data, and then an integer marking where is the top. Okay, it's basically saying, okay, where is the top of that array? And then there is a constructor here, it's a function, it's a method, okay, that basically sets the location by default to -1. So it says the top is -1. So when there is nothing, when the stack is empty, I choose the convention of setting top equal to -1. Just a convention, right? And then come remember the push and pop functions. I'm going to construct the push now. Basically, what is the push doing is adding a value, the stack, one of the books, the stack. And what it does is take the top, which is a counter, and it added one. So we are assuming somehow that we are one element at a time. Okay. The other thing that does, it checks if top is not the maximum, then assigns the value to the element of the array. Okay. If the stack is full, then it says the stack is full and it denies that operation. Okay. Examples of these are when you have the stacks functions, the operating system, you can see cases like this. Okay. So is that clear? If the idea of method confuse you or the idea of object confuse you, just think this as a function, and this is a structure, and you are implementing a function that takes the structure and adds one element into the array, and the value, if there is still room, and if not, you reject it. Okay. So the other function we want to implement is the pop. So retrieve one of the elements from the stack and release that space. Okay. So this is how the pop looks like. The difference with the push is that there is a type that is going to be returned, which in this case I'm going to use the value of what I'm returning as the value that the function is returning. So the first thing that you need to do is to check that I'm not dealing with an empty stack. If it is an empty stack, there is nothing to retrieve. Okay, so it's going to check if top is equal to -1. That was my convention for an empty stack. If top is equal to -1, it says the stack is empty. There is nothing that I can give you back. Okay. If it is not, then it assigns data, the content of the index of the array right at the top. It sets the top, the element to null. So basically, it says, okay, there is nothing there, and releasing that space. It says the counter to -1, so it removes or subtract 1, and returns the data. Okay, is that clear? So basically, you can think about this structure like a vertical array. So the space is there. Top is basically just saying which is the last element that was filled. 1, 2, 3. And every time that I do a push or a pop, this thing moves up or down, and the data is push or pop out of the stack. And this is max. I don't know. Yeah, max. It's the maximum size of the array. Okay. Questions? Yep. That's right. So when I do pop, so let's say this is the current status of the stack. So the top is pointing there, right? Now I do pop. What I get is 3. So return. Now I write null here. It's empty, and top points toward 2. That's when I'm decreasing here. Okay. Yeah. I think I had an example showing how it works. Yeah. So this is the implementation in the main function. First thing I do is I define. Remember, this is just the abstract type, right? There is no variable so far defined. So the first thing I have to do in main is define the variable a, which is of type stack. Okay? And then I'm going to push. So basically, let's do this step by step. So this is my stack A. So I'm taking the object A, which is of type stack, and I'm using the method associated with A, which is the push, which I define. And I'm going to push 3. So what it's going to do is that the first stack was initialized with top equal to -1. So it's pointing to nothing. It's the end of the array, right? So the first thing that it's going to see is, okay, I'm the end of the array. So I'm going to take the first element, put a 3, and increase top to 1. Okay, so that's the first push. And then it says 3 is pushed into the stack or whatever. Then it's going to push another time, and it's going to push the value 10. Okay, so top is here now. So it's going to push 10, and top is going to move to the next set. Okay, and 10 was pushed into the array. 1. Okay, so now top is here, push 1, top is moved up. Okay, so 1 was pushed. Now I'm going to start to pop things. And how it works, I just don't need to say anything because the structure itself is going to pop the last thing I push. Okay, so I'm just popping things, cout arrow a dot pop, and basically what it does is, okay, 1 is returned by that function, and top, which is the indicator where I am, is moved 1 step down. I do that again. Now 10 is pop out, top is moved down, and finally I do one more pop, 3 is pop out, and then top is put down. If I do one more pop, what is going to come back is going to say the stack is empty. There is nothing to pop. So that's the default constructor. So you can have other constructors, but the default constructor is the same. This probably is defined in a separate file. So this one is just before because I have one piece of code, but I can put this in a different thing, in a different module actually, and use all the strategies that we use with modularity and include that and all the types. Exactly. Okay. Say again, sorry. Here. Yes. Oh, yes, yes. So this number should match this number. If I choose to use this as 0, it's a convention sort of. And I choose -1 because, you know, arrays in C start on 0, the first. Yep. No, because this is true only if I try to access the stack when nothing was there. Because, let me show you. Now, there is no easy way to keep everything in the same slide, but for doing the pops, I did pushes, right? So what I'm doing here is I'm incrementing the value of top. So by default, when the stack was empty, top was equal to -1. After the first pop, top was equal to 0. because I did this in the push. Sorry, after the first push. Okay, and every time I do a push, these things go up by 1. Okay, and each time I do a pop, it goes down by 1. So it's subtracting 1 until it reaches -1. When it reaches -1, there is nothing else I can pop from that stack. Yes, because, and this has to deal with, the top is private to the stack function. So it's only the functions within the object that they can change top. Yes, because I'm basically defining a stack A of class or type stack. And as is stack by default or by definition will include the array and the index top. Okay?
There,
Mm.
but that off,
Mhm.
and it would actually make 9.
Yes, yes. Basically, you are setting the convention here, right? You will be wasting one element of the array. But yeah. Yeah. No, sure. Any other questions? Good. I know this is fun. Implementing these things are fun, and I cannot tell you how much fun is to debug those things. And that's why, yeah, you can imagine. And this was with an array, right? Imagine if I have a list of pointers. Can't tell you. That is fun. But because our friends from the standard template library from C++ decided that, okay, don't have too much fun, they already implemented this in templates. Remember what were the templates? The templates are kind of structures that has the feature of getting any type, the type that you define, and they will take that and implement the methods associated with that. So the STL or the standard template library has already implemented types, stacks, and queues. So you don't need to recreate the wheel, and you could use those. And basically, you define the class standard : stack, and all those methods, all the methods here, like it can tell you if the stack is empty, it can tell you the values, or like the top, or the push, or the pop. All that come for free by using the class stack and queue from standard template. Okay? I'm going to show you some examples. So here is a very quick example. So I'm basically taking the type SQ from the standard, defining my queue. Basically, my class is just a pointer to a string. So the queue will have associated a string with it. Then I have another pointer here, and my queue, and I'm pushing just the content of the pointer to the string. Because I defined the queue to be a pointer to a string, I had to push something of the same type, of course. Okay, and I can do something, and then I can recover the front of the queue. That's one of the nice things. You can get the front, you can get the end of the queue, those kind of things. You can pop things, and then just print whatever you get back. Okay, and I think that after seeing the first example, that, as I say, is implemented with an array, but it's just for the purpose of identifying which are the functions or methods associated with the stack or queue, then you can use definitely this one that has everything. And supposedly it's back. Yeah. That's the creator, I think, right? That's it. Yeah.
You see how template class. So a dequeue is one of these queues. In our implementation array, the element, this implementation they're using a queue. So this class has to contain a queue. That's that. You don't have to access it, but try to protect it.
Probably more details class, right? Is the option you're going to talk
Yeah,
about that?
definitely.
Yeah. So yeah, those things as well as the private and public parts we're going to discuss. Okay. So the template library has different kind of things. It has containers for the queues. So the D queue is a double-ended queue. It's like the one that I showed in one of the pictures. It has lists. It has maps and multi-maps. We're going to see some of them. It has just a single queue, the stack, different kind of maps, vectors, which we already saw, stack, and then different functions associated, and different algorithms and different modifiers that can be applied to any of those containers. Okay. So any questions? So this was kind of fast, but basically you can choose whatever function, whatever object you prefer, and just play with it without the standards. So let me talk a bit about another structure, which is a very nice structure. It's a bit more complex structure, but it's more powerful as well. It's a tree in general, or binary tree, as we're going to see here. And you can think of this as a more general case than a list. Okay. So the idea is we have nodes, and then we have pointers that can point towards other nodes. And so the point is that if it is a binary tree, each node can only have 2 pointers. Okay. And it looks pretty much as a tree. That's why it's called tree. So each branch can have leaves, and each leaf or each node in the branch can point toward other branches or nodes. Okay? So it's a linked abstract data structure composed of nodes. Each node contains a field, which is the value, and one or more pointers to other nodes. If the node has only 2 pointers, it's what is called a binary tree. Okay? It's a recursive structure in the same way that it was the list. Okay? And you can think of a list as a trivial tree. Just one tree with one branch. Okay. The nice thing of this is by having these structures, all what is graph theory, math, can be applied to this. And this is where the performance things will come in. Okay. So this is an example of an implementation of a tree. And I'm going to use here for the purpose, I'm going to use my own implementation, but I will show you how to do with the standard. So in this case, I'm going to use the structure. I'm calling the structure leaf. Okay, so that's the node if you want. And then the leaf has data, which is an integer in this case, and then it has 2 pointers, right and left. Okay, so it's another leaf. So it's the same type. Is where the recursivity came in place, and it can be pointing toward the left or the right. So it's a binary tree in this case. So each node can have a pointer of the same type of itself, but then left or right. Okay. Question? No? And then another pointer to the same structure. These are the public methods associated with the tree, the creator, the extractor. Then I can create other methods like find parent to go to the very top of the structure, add a tree, transverse the tree, as if something is in the leaf, in the node, delete a node, different ones. I'm just going to show you one example, which is how to add one node to the tree. Okay. So this is a function of the class or the object. I'm going to pass one integer. So these integers are like keys, are things that they should be in the tree, and I can look for them in the tree, and if they are, I can return, okay, this thing is already there, or not. If it's not, I can add. Okay. So the integer n is what I'm passing to the function. Then I'm defining an integer found to see if that was already within the tree. And then I'm defining pointers to the leaves of type leaves, to the parent, and to the next one. Okay. So I had a function find parent to find which is the root of the tree or the node. And if I found yes, then if I found that so that function will return to see, or will see if the data is already in the parent tree. If it is, it will return that it was found, and it says, okay, such a node exists already, so the data was already added there. If it is not, then I'm going to create a new node. So I create the variable t there, which is a new leaf, And this is the nice part. The data is filled with the value n that I pass to the function. Then the left and right pointers are importing to null. Okay? So basically, they are not pointing to anything. This is the last leaf in the tree. Okay? And then if the parent, so the previous one is null, then I point the pointer to the current node. Okay? Else you point the parent. This is an operator. It says, okay, if the data is greater than n, point the parent left to that node. Else point the parent right to that node. Why I'm doing that? Because I want to have the tree order. Let's say that this is the node. So let's say I put a 7 here as the first node of the tree. An input a 5. That will be go here with that. Sorry, an 8. And then a 5 will go, so the greater one go to the left and the smaller one go to the right. So you can have an ordered tree. So you know that if you are in this branch or in this node, whatever comes to the left has to be higher than this value. Whatever comes to the right has to be smaller. In the same way, if you are in this node, you know that your parent will be always higher than you. Okay, so this kind of trees are ordered trees or balanced trees. And again, they are very good for searches. So I can improve the performance of a search algorithm by just having ordered structures like this. Because if I'm looking for 5, when I come to this node, I know that I don't need to go and look at this node. I just know I have to go to the right. Okay. Questions? This is how the main function looks like. So I'm defining the tree T, which is of type 3. I'm defining a bunch of data. Okay. And then I'm doing a loop for feeding the data. And the only thing I need to do is take the tree, use the method add, and add the data to the tree. Okay, I'm defining this array with all this data here and there. And then I'm deleting one of the elements and transversing the tree. And basically, this is the important thing because it's the function. This is kind of a manual implementation if you want. Again, you can use, well, no, the standard template doesn't have a tree implementation. So you have to implement this from scratch. What it does have is the last thing that we're going to see today, quickly, which is a hash map or a hash table. These are very useful, again, structures because they allow you basically to create an association rule. So the idea is that you can map keys to values. So it's the same idea of dictionaries if you use Python. And it basically creates a function, which is called a hash function, to compute an index in an array and associate whatever is the input or the key to the data in the array. And again, the array can be pointed to structures and things complicated like that. Okay, so we're going to see how to implement that. And for this one, I'm going to just use the standard library. You can do again by your own. So in the standard template library, you have the object map, which basically you receive a key type and a data type, and then you can implement or use comparison functions. Okay, so this is an example of how you can implement one, just a string. In this case, the map will map a string with a grade list. Okay, so I have the grade list and the name of the person and then the grade. Okay, that's the character. Okay, so Sean got a B, then Sean improves the performance and got an A, so I can change that. It basically looks like an array. Okay. There are several functions that you can use when you create the grade list. It's like an array, but now the index that you use is something that can be more complicated, like a string, like a whole name key, right? So you have other functions that are created for you, like size, if the map is empty or not, or clear, which basically will delete all the elements in the list or map. So for instance, if I want to delete the entry of Sean, I just use graylist.grace and then the key I want to use. Okay? If that key doesn't exist, it will return an error and say, okay, that key doesn't exist. I can get the size of the map and say, okay, graylist.size, it will return the size, or I can just clear the whole list by using dot. No. This is just the last one. So this is another example, the same object. Basically, I'm asking if team is in the list, and if it's not in the list, it says it's not in the map. Okay, so that is the function find. Let me see what else I have here. So this is another example, same idea. I'm using a map for identifying countries with the population. So it's a string with a number, with an integer. And basically I'm filling them, so I'm inserting elements in the map, the name of the country and the population in millions or billions, I don't know, and so on. So I had several insertions. I can count how many of them I input, and then I can get the information back, of course. What else I can do? And find countries in the same way that I find names in the previous list. And we're almost there. So this is my last slide. And basically what I'm trying to argue here is the thing that I mentioned at the beginning. By defining the kind of a structure or the type of a structure, you will be able to perform better in solving the problem. And why is that? So we have different examples here, like arrays and hash tables. I think there must be a tree or a map somewhere over there. There's a self-balancing binary tree, which is a kind of tree, and list. The issue is, or the question is, how many operations I have to do in one of these structures to perform, for instance, an insertion, a deletion, forget about these two, a search, find the minimum, find the maximum, and the space that I use. The space doesn't change much, okay? So there is no win or loss there. But notice this is called big O notation. It's basically going to tell you, according to the size of the object, how many operations you have to do, okay? And look at that. The array, usually you have to do n operations to get an insertion, a deletion, or even find the minimum or the maximum. It can be even worse. But if you are dealing with a tree, the number of operations is order 1. And the number of operations for getting the maximum is log n, which is smaller than n. So this is where the performance comes in play. And where having these structures, which looks a bit more complicated at the beginning, will help you to improve how the codes work and how fast. Okay? And I think that don't have any questions, kind of are back today. Yeah, just in time. Had to rush a bit in the end, but